Hello everyone. Today's video will be about alternating series. We're going to define alternating series, we'll see some examples, we'll talk about how to tell if an alternating series converges, and finally we'll discuss how to approximate the sum of an alternating series. So first, let's define what we actually mean by alternating series. An alternating series is a series of the form sum of -1 to the n, bn, or sum -1 to the n plus 1 bn, where the bn are positive numbers. Now, why are series of these forms called alternating? Well, the -1 to the n or -1 to the n plus 1 will switch, or alternate, between -1 and 1. So, since the bn's are positive, the terms in these series will alternate between positive and negative. That's why we call these series alternating. Also, I just want to note that the only difference between these two forms is that one will have the negative terms in the odd positions, and the other will have the negative terms in the even positions. Now, let's see some examples of alternating series. We've already seen one example, namely the sum of -1 to the n plus 1 times 1 over n. And if you recall, we showed that the series converges by showing that the limit of the partial sums converges. Similarly, we could make this a series of the other form by changing it to the sum of -1 to the n times 1 over n. And the same way, this series is also going to converge, and it converges to the negative of the number that the last example converges to. As a final example, consider the series sum of -1 to the n plus 1 times n over 2n plus 1. This series is certainly alternating because of the -1 to the n plus 1, but does it converge? Well, notice that when we take the limit of the bn's, we get a half. Therefore, the terms that we were summing over don't go to 0, and so the series diverges by the divergence test. So, the question now becomes, how can we tell if an alternating series converges or diverges? The tool that we're going to use to answer this question is called the alternating series test, which says that if an alternating series, sum of -1 to the n plus 1 bn, satisfies two conditions, the first being that the limit of the bn's is 0, and the second being that bn plus 1 is less than or equal to bn for all n, or in other words, that the bn's are decreasing, then the alternating series converges. Before we apply the alternating series test to some examples, let's give some intuition for why this test works. So, if a series satisfies conditions 1 and 2 from the test, let's think about what the partial sums look like. Well, we start at 0, and then to find the first partial sum, we add b1. From there, to get the second partial sum, we subtract b2. However, since the bn are decreasing, we could not have made it all the way back to 0. Then, we add b3 to get the third partial sum. Again, since the bn's are decreasing, b3 is less than b2, and so we can't have made it all the way back to s1. And we continue this process, zigzagging back and forth, and the fact that the bn's go to 0 means that these zigzags will get really, really small, and will eventually approach some value s, which will be the sum of the alternating series. Cool. Now, before we move on to some examples, a couple quick remarks. First, the same test works for series of the other form, with -1 to the n, for exactly the same reason we just described. Next, we really only need that the bn's are eventually decreasing, or that bn plus 1 is less than bn for all n greater than or equal to big N, where big N is some positive integer. This is because if the bn's are eventually decreasing, then we can rip off the finitely many terms at the beginning before the bn's are decreasing and get a series that converges by the alternating series test, and then we can add back on the terms that we ripped off. Since adding finitely many terms to a series doesn't change whether or not it converges, our original series converges as well. On a similar note, how do we even tell if the bn's are decreasing? Sometimes it's obvious, but other times it may not be so clear. Well, if we were asked in Calculus 1 whether a function is decreasing, we would immediately think to take a derivative and see if it's negative. And we can do a similar thing here. So, if there's a differentiable function f, so that when we plug in n, we get out bn, Then we can use f prime of x to check if the bn's are decreasing. And for the last remark, notice that the alternating series test only tells us when an alternating series converges. So, how can we determine when an alternating series diverges? Well, we've already seen an example of a divergent alternating series. And how do we figure out that it was divergent? We use the divergence test. And this will be the tool we use in general. So, if when we take the limit of the bn's, we get something non-zero, then our alternating series automatically diverges by the divergence test. Now let's see some examples where we use the alternating series test. For the first example, let's take a look at the series sum from n equals 1 to infinity of minus 1 to the n times 1 over n. We already know that this series converges from before, but let's see if the alternating series test verifies this. So in this example, we have that bn is equal to 1 over n. So let's check the two conditions in the alternating series test. For the first condition, we take the limit of the bn's, and we want to get 0, and that is indeed the case for this example. The second condition is that the bn's are decreasing. And again, this is true in our example, since dividing 1 by n plus 1 will give a smaller number than dividing 1 by n. Therefore, this series converges by the alternating series test. Now for a slightly more complicated example. Consider the sum from n equals 1 to infinity of minus 1 to the n times n over n squared plus 1. Here, we have that bn is equal to n over n squared plus 1, so let's start checking the conditions of the alternating series test. First, we take the limit of the bn's as n goes to infinity, and we get 0, since the degree of the polynomial in the denominator is greater than the degree of the polynomial in the numerator. So condition 1 is satisfied. Next, we need to check that the bn's are decreasing. And this part's a little trickier than in the previous example. However, remember when we said that we could use derivatives to find when the bn's are decreasing? Let's try and use that idea here. Let f of x be x over x squared plus 1. Notice that when we plug n into f of x, we get out our bn's. Now, when we take a derivative using the quotient rule, we get out 1 minus x squared over x squared plus 1 all squared. To find when the bn's are decreasing, we want to know when this derivative is negative. So let's set f prime of x less than or equal to 0 and solve for x. If we multiply both sides by x squared plus 1 squared, which is a positive number, we get that 1 minus x squared is less than or equal to 0. And then we can solve for x to find that x is greater than or equal to 1, or x is less than or equal to minus 1. In particular, f of x is decreasing for all x values greater than or equal to 1. This in turn implies that the bn's are decreasing for n greater than or equal to 1, which is exactly what we wanted to show. Therefore, we verified the second condition of the alternating series test, and so we conclude that the series converges as well. Let's take a look at one more example. The sum from n equals 1 to infinity of minus 1 to the n times 2n squared over n squared plus 1. Here, we have that bn is equal to 2n squared over n squared plus 1. And now let's start applying the alternating series test. First, we take the limit of the bn's, and we find that the limit is equal to 2. In particular, the limit's not 0, and so automatically the series diverges by the divergence test. These examples should give you an idea of the different scenarios you could run into while applying the alternating series test. If you would like some more practice, try to apply the alternating series test to the following series. Remember, the important part is the process of showing whether or not a series converges, not the final answer. So, I'll tell you that the first two series converge, and the last series diverges. And now it's your job to prove it. Now that we've seen a few examples, I want to make a couple remarks. The first is that we just found that the sum of minus 1 to the n times 1 over n converges. However, if we drop the minus 1 to the n, we get the sum of 1 over n, which we already know diverges. So, it's possible for an alternating series to converge, even if the sum of the absolute values diverges. Recall, we have a name for this type of series. They're called conditionally convergent series. Next, notice that the alternating series test didn't give us a way to actually compute the sum, like we would for a geometric series, for example. In general, it's very hard to compute the sum of an alternating series, but there is a way we can estimate the sum. And for the rest of this lecture, we'll talk about how to do this estimation. So let's suppose that we have a convergent alternating series that converges to some number s. Then, as we've seen before, we can approximate s by the partial sums Sn. But we would like to get a feel for how close this approximation actually is. And as it turns out, if the series satisfies the condition of the alternating series test, then there is a nice way to estimate the error in this estimation, which we're going to write as Rn, which is the difference between s and the partial sum Sn. This estimation is given to us by the alternating series estimation theorem, which says that if we have a series which satisfies the condition of the alternating series test, then the error you get in approximating s by Sn is less than or equal to Bn plus 1. The proof of this theorem is fairly straightforward. We have that the error is equal to the distance between s and Sn. However, since the Bn's are decreasing, the distance between s and Sn must be less than or equal to the distance between Sn plus 1 and Sn. To see this, think back to the picture we drew when we were talking about the alternating series test. You can see here that the distance between a partial sum and the following partial sum is always smaller than the distance between the partial sum and the limit s. However, let's think about what happens when you subtract Sn from Sn plus 1. Sn plus 1 is the sum of the first n plus 1 terms, and Sn is the sum of the first n terms. So, if we subtract Sn from Sn plus 1, we're really just left with the n plus first term, which is exactly Bn plus 1, after taking an absolute value. And this proves the theorem. Now let's see an example of the alternating series estimation theorem in action. We know that the sum of minus 1 to the n times 1 over n converges. So now let's approximate the sum of the series with an error at most 10 to the minus 2. So how will we make the alternating series estimation theorem work for us? The goal is going to be to find an n such that Bn plus 1 is less than or equal to 10 to the minus 2. And why would this help? Because then, by the alternating series estimation theorem, we would have that the error in approximating the sum s by the nth partial sum is less than or equal to Bn plus 1, which we constructed to be less than or equal to 10 to the minus 2. So, we will have successfully bounded the error by 10 to the minus 2, just like we wanted. Now let's find this n. We set Bn plus 1 less than or equal to 10 to the minus 2, and we solve for n to get that n is greater than or equal to 99. So, let's take n is equal to 99. Then, just like we showed above, we have that the error in approximating the sum s by the 99th partial sum is less than or equal to 10 to the minus 2. And so, we have that the 99th partial sum, which is about negative 0.698, is within 10 to the minus 2 of the actual sum. And so we're done. Just a quick note, the actual sum of this series is minus natural log of 2, which is equal to negative 0.693, and so we were pretty close.